So before we start, let me just mention that homework 1 was released this morning. So we promise that you'll have 2 weeks. You'll have ever so slightly less than 2 weeks to do it. It's due on Tuesday at midnight, 2 weeks from now. We wanted to do it to give you a few days between the due date and the midterm, which will be on Monday, the week after. Okay, so today we're going to continue talking about integer programming. So last time Zico told you about integer programming, and I think did a masterful job of giving intuitions on how to solve integer programs. So why the LP solution might be integral, things like that, branch and bound. So that hopefully gave you a pretty good idea of how we approach solving integer programs. But of course, that's going to be useless if we don't know how to actually look at real-world problems and write them down as integer programs in a way that we can use the kind of fancy solvers that Zico mentioned and the kind of solver that you'll implement in the homework. So that's what we're going to do today. And I'm pretty excited about this because this gives me an opportunity to talk about some stuff that I think is really cool. So real applications that have societal impact and draw very, very heavily on integer programming. So these are things that in practice, people just write integer programs and solve them to address these real-world problems in practice. Okay, so let me just give you, reformulate the integer programming problem. And the reason I'll do this is that my formulation is going to be cosmetically slightly different from Zico's. Zico used this vector matrix kind of notation, which is very elegant, but I think this kind of notation will make it clearer when we talk about specific problems, what the variables are and what the constraints are. So here we're sort of writing down everything explicitly. We'll have constants, aij. So you can think of our matrix as this A where the entries are aij. And I goes from 1 to k, j will go from 1 to l. And we have another k constants bi. And then our variables, we're going to have L variables, which we denote by xj. Now, we're going to start by just thinking about feasibility problems, just asking, is there a solution that satisfies these linear inequalities with integer variables? We'll talk about optimization problems later on, but let's just write a feasibility problem with these notations. So what we want to do is find values for the L variables, such that for each one of the k constraints, we have that the sum over from j from 1 to L of aij, the constant, times the variable is at most some bi. Okay, so this is basically the matrix A times x is smaller or equal than b in matrix notation, just written explicitly. And for every j, the variable xj is an integer. Okay, so this is just another explicit way of writing down an integer program. So, just to make sure we're on the same page, Zico also mentioned this, but, this is sort of one way to write this that has inequalities in one direction. But of course, you can use the same thing to handle a bunch of other things. For example, if you wanted to write an inequality in the other direction, you could do that by starting from that inequality, multiplying by -1. You'll get an inequality in the other direction. If you wanted to have equality constraints, these are inequalities in both directions. If you wanted to have a restricted domain, so, x4 is between 3 and 27, you could write it with 2 inequalities plus this constraint that says it's an integer. Okay, so all of these things are, even though we wrote this in this pretty seemingly restricted way, you can write more general constraints by just playing with this type of formulation. Cool, so the first problem I want to talk about, I actually don't want to start from, it is a real world problem, but sort of not one with, you could even say it has societal impact, but not of the type that I was thinking about before. It's a problem, a puzzle that many people play, Sudoku, so Zico mentioned this last time. He also mentioned that Sudoku, even though it could be really hard for people, it's actually really easy to solve by integer programming, and that's exactly what you'll do in homework 1. What Zico didn't talk about is actually how to write Sudoku as an integer program, and that's going to be crucial for your homework. Right, so that's basically, there's two things you will need to do in that problem. One is you'll have to implement branch and bound, so that's the algorithm for solving any IP. But now to solve like this particular problem, you have to be able to write it as an IP, and that's the kind of stuff we'll talk about today for the whole lecture, and we'll start with Sudoku. So just to make sure we're on the same page, what are the rules of this puzzle? The board is 9 by 9. And it's divided, so you can think of like rows and columns in this board, but it's also divided into 9 3 by 3 squares. And then the rules are, you're given some squares that are already occupied by numbers, and then you have to fill all of the empty squares with numbers between 1 and 9, in a way that for every row, every column, and every 3 by 3 square, each one of the numbers from 1 to 9 appears exactly once in that row, column, or 3 by 3 square. Okay, so all of the rows, columns, and 3 by 3 squares all have 9 entries, and you want each one of the numbers 1 to 9 to appear exactly once in every subset like that. So this is like a well-known puzzle. And let's see how to write it as an integer program. So we'll jump right into it. So the first thing I want to tell you is how I define the variables, or how I think about the variables of the integer program. There's maybe like an interesting point here, which is, ultimately the integer program is just this, just math. But in order to understand it, we think of the variables in some way. We interpret them. So we say, oh, I think of the variable, like if it's 1, I think of it as this. If it's 0, I think of it as meaning that. And that will help us understand, the constraints and the objective function in this program. So my variables are going to be for every ij and k between 1 and 9. I have a binary variable, xijk, so superscript ij, subscript k, which is binary, so it's only 0 or 1. And I'm going to think of it as having the value 1 if I decided to put the number k into entry ij in my board. So I have this board which is 9 by 9, entry ij. I'm thinking of xij as being 1 if I decided to put k in that entry, ij, and 0 otherwise. Now, this is a surprising choice, I think, because, one might think the most natural variables to use here would be just variables xij that can take values between 1 and 9, and then it would just have the value that I decide to put in the entry ij. But it turns out that with these binary variables, it's actually much easier to write this integer program. It's much more intuitive. Okay, so we'll have these binary variables, xij, k. Now, I want to define 27 sets, which are basically defined the sets on which I have to satisfy this constraint of every number appears once. So the way I think of it is if I have this board, so I have this board which is 9 by 9, and it has these 3 large squares and rows and so on. So I think of it as like set number 1 is maybe the first row. So it's going to be the set that contains the entries 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, up to 1, 9. S2 will maybe be the second row and so on. Then maybe S10 will be the first column. Right? So it's so it's 1, 1, 1, 2, 1, 3, 1, and so on. And then I have a set like this for each one of the 3 by 3 squares. So every set like this is a set of indices that represents a row, a column, or a 3 by 3 square. So what's my integer program? Okay, these are sort of things that I've defined in advance. I have my variables. I've defined these sets in advance. Now here's the program. So I want to find values for my binary variables such that the following constraints hold. So the first constraint basically says that for every row, column, or 3 by 3 square, each one of the numbers 1 to 9 has to appear exactly once in that set. So let's see mathematically. It's saying for each one of my sets, my 27 sets, row, columns, and squares, for every number between 1 and 9, I need that the sum over all entries ij in the set of xijk, I need that to be equal to 1. All right, so again, intuitively, this is saying each one of the numbers from 1 to 9, each value of k like this, appears exactly once in the set st. Right? Is this clear? Because we're saying, we're looking at all of these variables, and we're saying exactly one of them for the set has to be set to 1. All of the others are set to 0. So this is saying, for this number, it has to appear in exactly one entry in the set. And we have a constraint like this for every number between 1 and 9 for the particular set. So this whole thing together, this is, you have many constraints here, and each one is saying, for a particular set and a particular number, that number has to appear exactly once in the set. Okay? Okay, so that's the first constraint. The second constraint is saying that for every entry has to have exactly one number. So I have to put some number in every entry. So this is saying for each entry I and j, if I look at all of the numbers from 1 to 9, one of these variables corresponding to the entry and the number has to be set to 1, and exactly 1. So this is saying I just have to enter some number into every cell. And finally, for, and the final constraint just says all of these variables are binary. They're all 0 or 1. So for every ijk, xijk is either 0 or 1. Okay, so, yeah.
So why is the second constraint necessary? I mean, how do you prove that these set of constraints are necessary and sufficient?
Yeah, that's a good point. So you're claiming the second constraint may be superfluous given this first constraint. I think that's true actually, right? Because we're saying like for each one of these sets, the set is of size 9. Each one of the numbers 1 to 9 has to appear exactly once in the set. You're absolutely right. So the second constraint will not, let's see.
No, but then you can have two numbers in the same set.
Oh, good. Right. Ritesh is right. So the danger is, right, I could put two numbers in the same square. Right. So the first constraint is telling me, like, if I look at all all of the entries in the square, right? So what's the danger? Let's say that I have a constraint that tells me in this 3 by 3 square, in this, each number has to appear exactly once here. But now maybe I want to satisfy the row constraint by putting in this entry 2 numbers. Right? If I didn't have the second constraint, I would be able to do that. Potentially satisfying the first constraint by putting all the numbers 1 to 9, but 2 of them here. And then that might help me satisfy the row constraint for this, that includes this entry. Okay, good. So that's why the second constraint actually is not superfluous.
No, but you can make it maybe at most 1.
You're saying the second constraint will make it most 1? Yeah, sure. I mean, that would be the same, right? So
So if you put at most 1, it reduces the constraint, but...
So you're suggesting for the first constraint to put it most? Yeah, but but it will be exactly 1 for every I and j, right? Because we have to
relax it by making it.
Oh, sure. Yeah, that's true. Right. Okay. So we could relax it, but the result would be the same. Right. Yeah, Jonathan.
How could you put 2 in one square if you have the binary constraint where there's always only one xijk?
Right, because these are 2 different variables. I could have xij3, xij5, which tell me, do I put 3 in entry ij? Do I put 5 in entry ij? Okay. Any other concerns about this program? Excellent. Okay. So just one high-level takeaway message here, and I'm actually going to give you a couple of these, expressed by Bender, which is just standard tricks for writing IPs in an easy way. So this is really something that's incredibly useful using binary variables. Like I said, in Sudoku, it would seem more natural maybe to have variables that say, xij is just the value that I want to put in ij. But then these kind of constraints that say, I need every number to appear once in a set and so on, would be much more difficult to write. So these binary variables give rise to a much more intuitive integer program. And in general, like we'll see a few more examples, but in general, this is true. So it's usually easier, I found, to write IPs with binary variables than variables that are not binary. Okay, so let's switch gears and talk about one of these real-world problems that I promised you. We'll talk about this one relatively briefly and then talk about another one in more detail. So this is the problem of kidney exchange, which seems like a problem from the world of medicine, and we'll see how it's related to both computer science and integer programming in particular. So just to give you a bit of background, as probably many of you know, when people have very serious kidney disease, often the best treatment is transplanting a kidney. And what's special about kidneys in particular is that people only need one kidney to lead a healthy life. So donations from living donors are possible. A living donor can donate one kidney and still lead a healthy life. Now, the problem is that often people, even when they have a willing living donor, like a close family member or friend, that donor may be medically incompatible with the patient. So there are many things that are tested, like blood type compatibility and tissue type compatibility. If any of these fail, then you have a problem. And that's where this idea of kidney exchange comes in. So in the most simple form, the idea is that you have a pair of donor and patient that are medically incompatible. So donor one maybe is the brother of the patient. He's willing to give one of his kidneys, but they're medically incompatible. Here's another pair, maybe a wife and her husband. So the wife is willing to give a kidney to her sick husband, but they're medically incompatible. But it so happens that donor one is compatible with patient two, and donor two is compatible with patient one. And in that case, they can exchange kidneys. Each donor gives a kidney to the other patient, and that way both patients get a healthy kidney from a living donor. So this is really the simplest form where you have a pairwise exchange, which we think of as a two-cycle. In practice, you can actually have long exchanges along longer cycles. So for example, you could have donor one giving to patient two, donor two giving to patient three, and donor three giving back to patient one. Okay? Now, in theory, you could have a cycle of length 40, right? You could have donor 1 to 2, 2 to 3, and until you go back to patient 1. There's actually a practical problem with very long cycles. It's kind of interesting. The problem is that you can't force a donor to give their kidney after their patient has received the kidney. So that means that if you don't perform all of the transplants simultaneously, a donor can say, "Oh, my patient got a kidney. Now I'm changing my mind. I don't want to. I don't want to go through this. Even though I can lead a healthy life, it's a pretty difficult medical procedure. So the donor can change his mind. So in order to prevent that, that would be a catastrophe, because then a patient, had this like loving, recruited this loving donor who wanted to help out, gave a kidney, but then the patient was left without a kidney. That would be a catastrophe. So in order to prevent that, all of the transplants happen simultaneously in practice. And that's why in practice, usually kidney exchanges restrict cycles to length at most 3, because that requires 6 operating rooms. And really, more than 6 operating rooms at the same time, that's tricky. You need an operating room for each donor and patient. Okay, so let's see how to think about this problem. We're in computer science, so we think of everything as a graph. So let's think about this problem as a graph. So the idea is as follows. The vertices in our graph, it's called the compatibility graph. The vertices will be donor-patient pairs. So every vertex is a pair of donor and patient. And we have a directed edge from one vertex to another if the donor of the first pair can donate to the patient of the second pair. Okay? And then, if you have a 3-cycle, that means donor 1 donates to patient 2, donor 2 to patient 3, donor 3 to patient 1. So this is an example from a specific kidney exchange that I'll talk about in more detail in a few minutes, the UNIST kidney exchange. It's one of their first match runs when they started running in December 2010. So the pool is still relatively sparse. The vertices here are the pairs of donor and patient. And you can see there are relatively few of them because things were just getting started. It's actually a directed graph. The dark part of each edge is the arrow, like the incoming part. But this is like a real-world compatibility graph from an early kidney exchange. Now here's the problem that we want to solve. So given a directed graph and the bound L on the length of cycles that we're allowed to use, like I said, in practice that's going to be 3, find a collection of disjoint cycles of length at most L in the graph that maximizes the number of covered vertices. Okay, so this is just saying we want to give kidneys to as many needy patients as possible. And so covering as many vertices as possible would do exactly that. And notice there's just one constraint here, that the cycles have to be disjoint, in the sense that I can't use the same vertex, the same donor to give kidneys multiple times. So this is a super interesting problem. Let me tell you one thing that's really interesting about it from the complexity viewpoint. So first of all, I claim that if L equals 2, if I'm only allowed to use 2 cycles, this problem will be easy, can be solved in polynomial time. Does anybody have an idea why? Deepak?
You just sort of cycle through the graph, and as soon as you find one matching pair, you can just pair them up, because you don't really need to worry about long-term planning of cycles.
So that's actually not true. So think about like a situation like this. So maybe we have like this pair, and so something like this. Right, so if this is the entire graph, being greedy might take this pair with and match 2 people, but that will not allow taking like the two cycles on the edges. Yeah.
If you take the, I guess, the person who can receive the least amount of kidneys and pair them with someone where they can get a kidney from, essentially do a greedy algorithm in that way.
So for that I don't have a counterexample off the top of my head. I mean, okay, I'm pretty sure that wouldn't work. I don't have a counterexample off the top of my head, but let's think about approaches that are not greedy. Richard?
This is maximal matching.
Excellent. Okay, so Richard said exactly the magic word, which is maximal matching. And the way to think about it is, if there are only 2 cycles, we can actually convert this to an undirected graph, where every edge corresponds to a 2 cycle, right? Like longer cycles won't help us. So we just look at undirected edges, which correspond to 2 cycles, and then the problem just amounts to a maximum cardinality matching in this undirected graph, which is sort of a famous problem. You can solve it via maximum flow or many other methods. So this can be solved in polynomial time. Excellent. Okay, so for the case of L equals 2, this is easy. Now another interesting thing, like here's where it gets interesting. If I don't give you a bound on the cycle length for unbounded L, the problem is also easy. So if I tell you like, now I'm not imposing any bound, the problem is going to be easy. However, if I give you a constant bound like 3, so I tell you you have to use cycles of length at most 3, then the problem is NP-hard. Okay, so this is like a really weird situation where if I really restrict the length of cycles, it's easy. If I don't restrict them at all, on the other extreme, it's easy. But like in the middle, the problem is actually NP-hard. And frustratingly, the L equals 3 case is actually the real world case that we care about the most. So in the real world case, this problem is actually NP-hard. Great, so with that motivation, so now we want an efficient algorithm for solving this problem in practice. And it turns out that writing it down as an integer program gives a really good solution in practice. So let me show you how to do that. It's actually a very, very easy integer program if you just write it naively like this. So what I'll do is, for every cycle of C of length at most L, I denote the length of the cycle C by LC, and the length will be at most L, so that's my bound. I'm going to have a variable xc, which tells me, do I include cycle C in my cover or not? Okay, so, and the idea is, if I take a cycle of length C, I'm going to add its length to the size of my optimization objective. The only catch is I have to make sure the cycles are disjoint. So now this is an optimization problem. The objective is maximize the sum over all cycles, xc times lc. So if I decide to take the cycle, I put a 1 here, and then I get the length of the cycle. Okay, that's my optimization objective. Now what are the constraints? The only sort of non-trivial constraint is saying, for every variable, it can't belong to several different cycles that I've decided to take. Okay, so this is just saying the cycles have to be disjoint. So mathematically, for every vertex V, the sum over all cycles such that V belongs to the cycle of XC is at most 1. Okay, I may not take any cycle that contains this vertex, but I could take at most 1, and that way I ensure that these cycles are disjoint. Yeah.
How do you efficiently identify the bounded length cycles that's violated?
Excellent. So remind me your name? Zia. So Zia is asking, how do I efficiently identify the bounded length cycles? So notice that if the bound on the cycle length is 3, then the number of cycles is polynomial in the number of vertices. Right? It's going to be, at most n choose 3. So it's actually not going to be huge. Right? So I can go over all of the possible, so just identifying the cycles is not a big problem. The problem, however, is that, it still could be a pretty large number. And in this program, I have a variable for every cycle. Right? So that's it's less about going over the graph and writing, writing down this program. You just have to go over the graph. Okay, it's going to be pretty big, but not a big deal. But now I have this program, right? Solving this is NP-hard. And I have this program where the number of variables depends on the number of cycles of length at most L in the graph. Now that's bad. Okay? So this is where it gets really messy, and it actually gets even worse. And the reason is that in addition to cycles, in the real world, you can also have chains which are initiated by altruistic donors. And these chains can actually be longer because the idea is, the donor gives to some pair, and then that pair gives to another pair. But here you don't have to do it simultaneously, because if somebody changes their mind, the chain breaks, but nobody lost the kidney, because the whole thing started with an altruistic donor. So these chains can actually be longer than 3. Okay? And then if you want to take chains into account as well, then you're really in trouble, right? The number of variables is just going to be really large. So in practice, I'll just say one word about this. The first approach people use to solve this problem, this dates back actually to work from here by Thomas Sandholm and Avram Blam, and Thomas's student at the time, David Abraham. So it writes exactly this integer program, but it uses a technique called column generation, which basically relies on the fact that in the optimal solution, most variables will be 0. So you just add variables incrementally, and in some way you prove that you've reached the optimal solution, even though you still haven't even looked at many of the variables. That's the very high level idea behind column generation. But this is just to say, this is the actual integer program that is solved in practice. However, if you just feed this into Cplex, you're going to be in trouble. So you do have to work a bit harder in order to get this to scale to large kidney exchanges. So just to say a few more words about the practical aspects. So one example application, like I said, is UNOS, which is the United Network for Organ Sharing. So this is the organization in the US that is in charge of organ transplants, all kinds of organ transplants, in particular kidneys. And they're running the US National Kidney Exchange, the UNOS Kidney Exchange. So right now, this is the largest kidney exchange in terms of the number of participating hospitals. I think the number right now is 160 something, which is around 2/3 of all transplant centers in the US. And the algorithms for this exchange are run from CMU by Thomas Sandholm's group. Okay, so this exchange relies on algorithms that are based on integer programming and were developed at CMU and are still being developed all the time and improved. In addition to this very basic problem, there are many, many difficulties that come up, uncertainties that come up. You don't know if matches will succeed. There are dynamics with patients arriving and departing over time and so on. So there are many, many complications that arise in practice, which if you can take into account in your optimization, give you even better results than just the abstract program that we talked about. So this was the abstract program that actually was the starting point. But then, there's a lot more work building on this. But again, this is integer programming is what's solving these problems in practice, and moreover, it's integer programs developed at CMU. Yeah.
If you go back to the other slide, why is C binary in this case, 0 or 1? I guess what's a C of 0 mean?
So it means I decided not to take the cycle C. So XC1 means I decided to include C in my cover, and XC0 means I decided not to include it.
And then X itself is 0 or 1.
Yeah, so X, I just have for every cycle C, I have a variable X sub C that refers to that cycle. Okay, so C is not going to have a value which is 0, 1. It's just like in our minds corresponds to a cycle. This is again, this gap between the math and our interpretation. So we just have a bunch, like if we have a million cycles in the graph, we just have a million variables. They don't actually have they don't have something that connects them to a cycle. But in our mind, we're connecting each one of them to the cycle, which is what we're reminding ourselves with the subscript C. And then the constraints are built in a way that, the constraints actually depends on which cycle is associated with each variable. Okay, but C is not actually going to take a value. It's just like tells me which cycle this variable X is associated with.
All right, or in here you say like for all C, comma, XC in the set 0, 1.
Yeah, so for every C I have a variable XC, and then the variable XC will be in 0, 1. Awesome. Okay, so I want to spend most of the lecture actually talking about another real-world example that is even closer to my heart, the example of fair division. Specifically, we'll talk about fair division of indivisible goods. And I want to really show you different things in fair division, and I'll use it as an opportunity to show you different tricks in integer programming. But it will be a nice opportunity to learn a few things about fair division as well. So it sort of seems like a win-win. Okay, so here's the setting that we'll be talking about for the rest of the lecture. We have a set of players that we denote by capital N, and that's the set 1 to n. So these are the players. And then we have a set of m items that we want to divide between the players, and we'll denote them by integers 1 to m. Now, player 1 has a value Vij for the item j, and these values are given to us. Okay, that's the starting point of the problem. Now, our goal is to divide the items between the players, which we think of as a partition of the items A1 to AN, where AI is the bundle of items given to player I. Now, we say that a partition like this, A1 to AN, is envy-free if the following property holds. So for every two players, I and I prime, the value I has for his bundle is at least the value I has for the bundle of player I prime. Okay, so this means, we'll look at the math in a minute, but this is sort of conceptually, and this says every player prefers his own bundle to the bundle given to any other player, or in other words, no player would want to swap his bundle with any other bundle that was allocated. Right, and mathematically, the way we're writing it is, the value of I for his bundle is the sum over all items j in his bundle of Vij, and the value of I for player I prime's bundle is the sum over all of the items in the bundle of I prime, again of Vij. Okay.
Do you have some further assumption on these AIs when you work with them?
No, it's just a partition of the items.
Oh, sorry, I mean the values.
Oh, so there's an implicit assumption here? Oh, the Vij specifically, no. There is a very big implicit assumption here that the player's value for a set of items is the sum of individual values for the items.
But
Other than that, there are no assumptions. This additivity assumption is something I can talk about for hours, but I won't. Yeah.
I don't know if this is what you were just saying, but is it definitely possible that this can happen, or is it not always possible that
The evaluations are additive? So in practice, there are many examples where this wouldn't happen. So for example, think of, the terms for, one term is complementarities, where you have two items that complement each other. So for example, if you have a left shoe and a right shoe, you have no value for one shoe if you don't get the other shoe. Right? So here, your value for both is not the sum of values. Or another example is substitutes. If two items are identical, you only need one, your value for both won't be the sum of values.
I think I wasn't clear. I meant, is it possible for each combination, is it possible that there is a set of bundles, or how do I say this? Is it possible that it's impossible for
an envy-free allocation to exist? Yeah, sorry. So the question was can we always find an envy-free allocation? And the answer is definitely not. So think about two items where both players prefer the same, two players, two items, both players prefer the same item. I give that item to one player and then the other is envious. Or an even more extreme example, only one item and two players. I give the item to one player, the other is envious. So that's a great question, and the answer is definitely no. So I can't always satisfy envy freeness. In fact, what we're going to try to do is write an integer program that tells me whether an envy-free allocation is feasible. Okay, but yeah.
Can two different players have different values for the same item?
Yeah, so the Vij could be like for two different values, I and I prime, two different players, it could be two different values. Yeah. So players could have different values for the items, and two players can have different values for the same item. So I'm not making any assumption about the Vij's specifically, except that there are no negative. Yeah. Sorry, so which equality do you want to change to?
I and I prime.
Yeah.
What I believe is only an equality might hold. If there ever a case wherein an inequality would satisfy the envy.
So an equality is an even harder constraint to satisfy.
But that would be the only feasible one, right? Because you can always switch I and I prime, and then the only thing that satisfies both of those is the equality.
Yeah.
The I prime and the right side of the equation is only the bottom.
Yeah.
So it's not symmetrical.
Yeah, so this holds for any two, in this definition you can switch the two players as well. Okay, so this holds for any two players I and I prime. Right, so you could have a situation where like this holds in actually the example I'll give in 5 seconds will hold in a strict inequality. Okay, so let's see an example where this is a strict inequality. So we have two players, and we want to divide this estate. So the estate has a fancy house. It has this stamp, which is actually a very valuable stamp. That's the black penny. It has 3 cars and 2 pieces of jewelry. And these are the values of the players to the items. So this row is the values of player 1, and this row is the values of player 2. And I want to look at this allocation where I give the house and the black penny to player 1 and everything else to player 2. So now notice that the value player 1 has for his bundle is 30, and the value 80, and the value player 1 has for the other bundle is 20. Okay, so now we have actually a strict inequality where this is 80 and this is 20 for the pair of players 1 and 2. But now this also has to hold for 2 and 1. Okay, why does it hold for 2 and 1 where I is 2 and I prime is 1? Why does this hold? Because player 2 has a total value of 88 for his bundle and 12 for the other bundle. So again, like if I equals 2 and I prime equals 1, this would be 88 and this would be 12. Okay, so this is actually an example where I can satisfy envy freeness. I'm satisfying it with a strict inequality. I won't be able to satisfy it with inequality. Yeah, Priya?
Could you give us some intuition for why we have to require the valuations to be non-negative? Like what breaks if something is...
Yeah, so here actually nothing would break because I'm not even guaranteeing to you the existence of an envy-free allocation. Some of the other things we'll talk about later will break, so we can revisit that later. Okay, so here's how we would write this program of like, tell me if there is an envy-free allocation as an integer program. So again, we do the magic of binary variables, where variable xij is 0 or 1, and it's 1 if I decided to give item j to player I. Or in other words, it's 1 if I put j in the bundle ai. So here's the integer program. I want to find variables to satisfy the following constraints. The first constraint is the envy freeness constraint. So what it says is for every 2 players I and I prime, and all I've done is I've just written this constraint in a linear way. Right? So this was saying I'm summing over all of the items in AI, the value. The way to write this is I'm summing over all of the items, but multiplying by the value by xij. So xij tells me whether I actually decided to give item j to player I. If so, player I derives value from that item. Okay? So these are constants, and these are my variables that tell me if the item is actually in the bundle AI. And so this is saying I want the value of I for his bundle, right, which is determined by these variables, to be at least the value of I for player I prime's bundle, which is determined by these variables with I prime instead of I. So now they're going to be 1 if I decided to give the item to I prime, and this thing will correspond to the value I has for the bundle of I prime. Yeah.
Can you repeat why it is a Vij and not a Vi prime j?
Yes. So Dimitrios is asking why is this Vij not Vi prime? So this thing, oh sorry, here you mean. Yeah, so what I want to say, like if you go back here, this constraint is saying the value I has for his bundle is at least the value I has for the bundle of I prime. Right, so here we've used Vij because we want to ask what's the value I has for the bundle AI prime. Okay, and for the same reason I'm using I prime, I here and I prime here. So this is the value to I for the allocation to I prime. Okay, okay, so that's the NV-freeness constraint. The second constraint is an easy one that just says every item has to be allocated to exactly one player. So notice I'm forcing every item to be allocated. Otherwise, it would be very easy to find an NV-free allocation, but by not allocating any item. So then everybody has an empty bundle and nobody is envious. But I'm forcing all of the items to be allocated. And finally, all of the variables are in 0, 1. Okay, so that's the integer program. Of course, the problem which we already talked about a few minutes ago is that an NV-free allocation may not exist. So this program will tell us, we'll try to find one, but in many situations, like the examples that I gave you, it may not find a feasible solution. So at this point, I want to, before we talk about more fairness notions and more integer programs for them, I want to do like a 5-minute detour through, or maybe even 10 minutes, through a really, really cool fact or like truth about integer programs and constraint satisfaction programs more generally. So to see the intuition here, I want to go through 2 polls and get you thinking a bit. So we said, okay, we might have a problem in the worst case that there is no NV-free allocation. But let's imagine that we're not, we don't get to construct our example. We're in this random regime where every player has a random value, Vij, for player j, which is drawn uniformly at random and independently in 0, 1. So every player has a random value for every item independently in 0, 1. That's the regime. And the question is, if the number of items is half the number of players, so M is the number of items, N is the number of players, the number of items is half the number of players, what's the probability that when we draw values in this way, an NV-free allocation would exist? So this is poll number 1. I'll give you like a minute to think about this. And actually, because you can see the poll on Piazza, I'll go back to the definition of NV-freeness on this slide. Yeah.
At least on mine, I only see one option that has all of the things at the same time.
Oh. I mean, on my screen it seems okay. Is everybody seeing like all of the options okay?
Yeah, I'm also only seeing one option. It's weird on the phone.
Okay. Well, I guess I'll just choose the one option and I'm right no matter what.
Mine looks fine on my phone.
Oh, really? No. Can you try like refreshing it? Or?
Yeah.
Is it the same thing for the other poll?
Good question. Can you go back to the slide? Yeah, it's the same for the other one too.
Yeah? Okay, so we'll ignore like the distribution of answers. The important thing is like to vote. So 10 more seconds. Okay.
I have to like change the file.
Sorry.
Give me a few more seconds.
Oh, sure. Good? Okay. So, good. So we have a plurality vote for the right answer, which is 0. I don't know how to interpret this with the bugs that people experienced, but it's actually a trick question. So why is it 0? Yeah, Michael.
If you don't have anything and your value is like likely to be bigger than 0, of course you want what the other person has.
Excellent. And your name is Michael, right? Yes. I remember it was like more complicated and I mispronounced, so we settled on Michael. Yeah, that's exactly right. What Michael is saying is like if there are fewer items than players, some players will have no items, but they're with probability 1 they'll have non-zero value for the other items, and therefore they'll be envious of any player that did get items. So if you have so few items that you can't give at least 1 item to each player, there's no way you'll get envy freeness unless there are 0 items. Okay, so here's a difficult poll. This one was the easy poll. So this is the same question, same regime, but now the number of items is much larger than the number of players. Make it like as large as you want. Or fix the number of players, take the number of items to infinity. What's the probability now that we have an envy-free allocation? And extra credit if you can give an explanation for why your answer is true. I mean, I'll actually be really excited if somebody can give me an explanation for the right answer. Yeah.
On the poll, it says n over 2, not
n over 2. It says poll 1, right? Let me just edit this.
Oh, it's n greater or greater.
Oh, right.
Much greater.
Thanks. And that's what happens when you clone polls and then forget to change the... Ten more seconds. Okay, excellent. We have almost 1/2 for the correct answer, which is close to 1. So now Now the challenge. Can anybody give me an explanation for why?
I just can try. It's not a rigorous one, but just.
Okay.
So let's say we make a table. There is our n people, and we have a lot of other items.
Okay.
And so for each item, we pick a people for who's it's maximizing.
Excellent.
Okay. And then if we have a conflict, which is we have like two maximization in the same column or row, whatever you place that, we just generate more goods unless these.
So I mean, you will have a conflict with probability 0 because these values are uniformly distributed. So don't worry about conflicts. But great. Okay, so the idea is perfect. And now, so then what's the next argument?
Yeah, and then like for each person, we just pick those goods for like. That maximizes the profit for that person, and like obviously you cannot have a contradiction with freeness just because each person gets the maximized items.
Oh wait, so you're actually saying something different from what I had in mind. So you're saying for each player, we're going to give him his favorite items among all of the items, basically.
Yeah.
Okay, yeah, I guess it's sort of a dual approach. Yeah, let's see if this. Yeah, I think this will. Yeah, yeah. So I think this will.
I mean, it's close to one. Okay. It's close to Tunisia.
Yeah, but okay, but this is, I guess, right. Yeah, but here in this approach, like, you will have. So when you say like, I want to give each person's favorite goods, so you're saying, okay, but then now we do have to worry about conflict. So in your approach, like, we do have to worry about that because it's not about equal values. It's about two players placing the same items in top positions.
This is what I mean. So if two items are in the top for two players, they generate more examples until it will.
So it's a nice idea. I think there's even like a cleaner argument here. Yeah.
Let's say that you have a distribution, and then you have two people, one person agrees with another person. Since there's so many items, there's likely like a pair of items that you swap, where they have inverse values, and so because of that, if you swap them, you can start reducing the number of
Yeah, so, I mean, I think it's good intuition, but I don't see how it would lead to an easy proof for this. Yeah.
It seems that if we have a lot of items, the problem becomes continuous, which means that if we can divide items arbitrarily, which is what I mean in the continuous case, if I thought someone whose item has more value than me,
So it's actually interesting because in the continuous case, it would be a special case of a problem called k-cutting, where an NV-free allocation always exists. So I think an argument like that could work, but again, I have in mind like something even simpler. Michael.
Just give each item to the person who likes it best.
Excellent. Great. Fantastic. And do you have like a follow-up on why that would work?
Right. So as n goes to infinity, everyone will get the same number of items.
Excellent.
And the expected value of your items will be higher than your expected value of anyone else's items.
Amazing. Okay, great. Fantastic. So that's exactly right. So what Michael is saying is the following fantastic answer, which is our algorithm is the following simple algorithm, which is sort of the dual. Right, so the idea is each item will be given to the player who likes it the most. Okay, like look at all of the values Vij for item j, give it to the I that maximizes these values Vij. So now, and you followed up with exactly the right argument, which are every player is equally likely to win each item. Right, so the size of each player's bundle will be more or less m over n. But you have probability of 1 over n to get each item. And if you guys have heard the term measure concentration before, I mean, it's very easy to prove that like the number of items that you'll get is very close to the expectation, which is m over n. So everybody will get bundles of almost the same size. And then the second argument is, for the items in I's bundle, his expected value for them is very high because he got them because he was like, we took n random numbers and he was the highest of them. So the expectation is actually n over n minus 1. So he has like a value very close to 1 for each item in his bundle. For each of the other bundles, the only thing we know is that he wasn't the highest. So without knowing anything, his expected value is 1/2. With that knowledge, maybe a bit less. But in any case, like for all of these other items he didn't get, his expected value is only 1/2. So again, like the bundles are almost of the same size, but for my bundle, I have very high expected value for each item. For every other bundle, I have expected value only 1/2, and therefore my total value will be higher than any other bundle. So that's really great. Okay, good. So, so this is sort of tricky, but here's the intuition I want you to take away from this. So in this problem, there are sort of two extremes. One is the problem is over-constrained. I don't give you enough items to satisfy the constraints in a sense, and then there's no way there'll be an envy-free allocation. That was pole number 1. Pole number 2, the intuition is that the problem is under-constrained. I give you so much freedom that it's very easy to find an envy-free allocation. In fact, like this very simple algorithm is very likely to find it. So this is like a case where the problem of finding an envy-free allocation is very easy. And the big question is what happens between these two extremes? Right, so like there's under-constrained, over-constrained, what happens in the middle? Yeah?
What happens if in both two players happen to have the same value?
So that will happen with probability 0 because their values are continuous distributions over 0, 1. But even if not, just give it to one of them at random, you would still have probability 1/n of getting the item. Yeah.
In pole number 1, what if every player assigns a value of 0 to?
So you have a probability 0 of assigning value 0 to any item because again, because I mean this distribution has measure 0 on every point. So there's like probability 0 that you'll have a specific value for an item, including the value 0. I mean, this is like, it's not, it's like subtleties. Okay, so let's get back to the big picture. So what happens between the two extremes? So here's what happens, and I want to explain this graph to you because I think there's something really amazing that's happening here. And like I said, it's like a general phenomenon that is really, really amazing. So what this graph is showing is the probability of existence of an envy-free allocation under the regime that we talked about when you have exactly 10 players. And what we're varying on the x-axis is the number of items. And then the red line is showing the probability of an envy-free allocation existing. So if m is smaller than 10, then there's no chance of an envy-free allocation. That was pole number 1. So this is this side. If m is very large, then the probability is 1. The problem is under constraint. That was pole number 2. But look at what's going on in the middle. So there's some point, which is around n log n, where the probability jumps very sharply from 0 to 1. Okay, so we knew it would be 0 on one side. We knew it would be 1 on the other. But you might think, okay, so then, there's some smooth transition between the two extremes. But no, the probability jumps very sharply between 0 and 1. So that's the red line. Now, the really amazing thing is that if you give these random problems to CPLEX and you plot the computation time, the time it takes CPLEX to solve this problem, you get this dotted line. So this is like the running time. And look at what's happening here. So the running time is very, very, very low, except for this jump. So it's like very, very low. It jumps around the transition point, and then it goes very sharply down again. Okay, so what this is saying is the following amazing message, I think, that we know where the hard problems lie. And they lie exactly around this threshold where the problem is neither under-constrained nor over-constrained. So essentially, if the problem is under-constrained, it's going to be very easy to find a feasible solution. You start running branch and bound, you'll get an integral solution, bam, done. If the problem is over-constrained, you'll start running branch and bound, you'll get LPs that are not feasible, you're done. I mean, actually, the methods in CPLEX are more sophisticated, but that's the intuition. It's going to be like very easy to find that there's no feasible solution when the problem is over-constrained. So the only place where integer programs are actually hard is around this point where the phase transition happens, where they're not under-constrained or over-constrained, where the probability of actually having a solution jumps very sharply from 0 to 1. Now you might say, okay, this is just one problem, this problem of finding envy-free solutions. Why are you saying it's a general phenomenon? So that's the amazing part. It turns out this exact graph happens over and over in almost every integer program, and more generally in constraint satisfaction problems. So here's the original paper, the original graphs from the original paper that noticed this phenomenon. It's a paper from IJCAI, which is a big AI conference, 93. And they actually showed this for graph coloring. So they looked at 3 coloring and 4 coloring. And look, I'll try, the resolution is very bad because that's the copy of the paper that's available online. But I'll try to explain to you what's going on. It's the exact same graph that we saw before. So what this is showing is you're fixing a certain number of nodes in your graph. Now in graph coloring, what determines whether the problem is under constrained or over constrained, like how constrained it is the number of edges per vertex, or the average degree. So what we're varying is the average degree of the vertices on the x-axis. And then when the average degree is very low, there are few edges in the graph, the problem is under constrained, the probability of having a feasible solution in graph coloring is 1. So it starts at 1. When you have a high average degree, the probability is 0. But then the probability drops very, very sharply between 1 and 0. Because it's in the other direction, but again, this very sharp phase transition. And what we're showing is that this actually, the point where this happens actually doesn't depend on the number of nodes in the graph. So if you take 81 nodes or 144 nodes, you get the drop exactly at the same point. So there's this critical parameter, which is like the average degree, and that's what really determines where this transition happens. And the same thing happens with 4 coloring, but at a later point. Right? So now we have more freedom, so the problem would transition at a higher average degree. But still, exact same thing. And then if you run algorithms for solving these problems, these random problems, then you get this running time graph where there's a huge jump exactly at the point where the transition happens. Exactly at this critical value for the parameter average degree. And and these graphs appear in many, many, many problems. So it really gives, I think, a beautiful idea of what makes integer programming hard, or like where the hard problems lie. Yeah.
Does the previous, the graph in the previous slide scale similarly, or no?
Yes. So this one is for n equals 10. It also looks similar, and the thing is, like here, unlike the other graph, it's this is looking at a parameter that's independent of the number of vertices. Here, the y-axis is actually plotting m, and the critical point is around n log n. So the critical point would move on this graph as you increase n, but you'd still get like the same sharp phase transition, the same running time.
Is there an intuition of why it is so? Because like in graph coloring, it's a local thing, so it doesn't matter the number of
yeah.
But here.
So here, I think the intuition is coming from our polls and the under constrained, over constrained thing. So it's just like at some point, you can prove this, and it's proven in this paper. You can prove that if the number of items is asymptotically smaller than n log n, then it's very unlikely to have an envy-free solution. If it's asymptotically larger, then it's very likely via the algorithm that we talked about. And then, so this you can prove actually asymptotically. But the interesting thing is, in practice, it's not an asymptotic thing. It's a very sharp thing at this particular constant times n log n threshold. Yeah, Jonathan.
What were the axes on the right graph there? The next,
so it's again like the x-axis is again the same thing, which is the average degree of the vertices, and the y-axis is the running time of some algorithm they use to solve these instances. Okay, cool. So I'm definitely not going to have time to go through all of my slides, but I want to show you at least one other fair division approach and the integer program to solve it. So this is another approach that's very close to my heart. It's a concept called the maximum share guarantee. In order to motivate it, I want to show you an example. So this is an example where we want to divide an amazingly valuable art collection between, let's say, 3 sisters. And what I'll do is the following thing in order to divide this art collection. And I won't actually do this just to motivate the problem. I'll go to the eldest sister. and I'll tell her, look, I give you the privilege of dividing the items into 3 bundles. So you get this privilege, but then your sisters will get to choose bundles before you. So you're dividing, but then they choose before you, so you get to choose last. How do you want to divide? So the sister says, well, okay, first I need to evaluate the items. So she's looking at the items, and she's like, well, the Mona Lisa is obviously very valuable. Let's say $50. Girl with the pearl earring, also beautiful picture. Maybe it's like 30 billion instead of 30. $30. The Scream, it's like an interesting picture, but maybe not something you would want in your living room. So $3. This is actually a Jackson Pollock painting, but it looks like garbage. So $2. And then, like maybe $5 for the Picasso and the Van Goghs. So what she can do is she can divide the items into bundles in the following way. So she puts the Mona Lisa and the girl with the pearl earring each in its own bundle, and then everything else in one big bundle. And in this way, her minimum value for any bundle is $20. So this way she can guarantee to herself that no matter what her sisters do, she will get a bundle worth at least $20. So now the sisters go ahead and choose. So maybe the green sister chooses this large bundle, and the red sister chooses the Mona Lisa, and then the one who divided, who gets to choose last, chooses the last one, the girl with the pearl earring, which is worth $30, almost a third of the total. So that's pretty good. But now this red sister, the one who chose second, can say, hey, this is really not fair to me, because here are my values for the goods. So, when I chose, I was only able to choose between these 2 things that are both like almost worthless to me. So I ended up with like $3, which is like a very small fraction of my value for everything. If you gave me the privilege of dividing the goods, I would divide them like this. And in this way, I would be able to guarantee to myself a value of $30, no matter how my sisters choose. So this red sister is really pissed off for not having the privilege of dividing the items. Even though she would have gotten to choose last, it would still be much better for her. So the question is, can we simultaneously divide the goods in a way that each player receives at least as much value as what she would have guaranteed to herself if she were the one to divide, but then chose last? Okay, that's the idea behind the maximum share guarantee. So let's write this formally. The maximum share guarantee, this is, by the way, a concept due to an economist called Eric Budish. So the maximum share guarantee of player I is the maximum over all partitions of the items x1 to xn into n bundles. So player I partitions the items into n bundles, but then gets to choose last, which means he enjoys the value of the least valuable bundle among these n bundles in the partition. So this is the value that I would be able to guarantee if she were the one to divide the items into n bundles and then chose last. And notice that this is defined for every player separately. Cool. So what I want to show you first is that we can actually compute the maximum share guarantee of player I as an integer program. By the way, doing this is NP-hard. You can very easily reduce the partition problem, which is a well-known NP-hard problem, to this one. So this is NP-hard. I want to show you how to write this as an IP. And I think maybe one thing that's surprising about the fact that this can be written as an IP is this objective function. Right, so when we talked about IPs so far, we talked about objective functions which are just maximize or minimize some linear thing. Now the objective function, we're trying to find a partition that optimizes this objective function, which is a max-min objective function. Right, so this doesn't seem like something that you'd be able to fit into the IP framework. And what I want to show you is that in fact you can, and it's actually very, very easy to do this. Okay, so how do I write this as an integer program? So the first thing is my objective function is d. D is some new variable, and the only thing I'm trying to do is maximize d. And the idea is that d will capture this thing, the minimum over bundles of the value I has for the bundle. So by maximizing d, I would be maximizing the minimum. So how do I get d to capture this minimum? I do this with this first constraint that says for every bundle, now remember, what is this? let me actually say a few more words about this. So like before, Vij is the value I has for item j. Yjk is 1 if I decided to put item j in bundle k and 0 otherwise. So it's similar to these xij variables we had before, but now we're not allocating items to players, we're putting them in bundles. So I'm calling it yjk, putting item j in bundle k, but it's basically the same as before. So this thing, this is the total value I has for bundle number k. Okay, so this thing is the total value I has for bundle number k. And what this constraint is saying is for every k, for every bundle, the value I has for bundle number k is at least d. Okay, so let's revisit this constraint in a minute. Let me just mention the second constraint, like before, just says every item has to be put in some bundle, exactly like before for envy freeness. And the last constraint says all of the variables are binary. So why does this work? Yeah.
So in the first constraint, it should be for all I as well.
Right. No, sorry. We're fixing I. So this whole thing is trying to maximize the maximum share of player I. So we fixed I, and we're going to solve this program for every I separately. Okay. Okay, so this is just like every I separately has to solve this program, which is his particular. He gets to divide. There are no other players in the world, and then he'll just get to choose last and get his last bundle. So we're only looking at I. We only care about I, and this is specific to I. Yeah.
So you're maximizing essentially. Well, D is basically saying every bundle needs to be greater than this.
Exactly. So let's revisit this constraint. That's exactly what I wanted to get back to. So why is this working, right? What's happening is our objective function says maximize D. So so our solver will try to set D as high as possible. Now the thing is, D is being constrained by I's value for every bundle K. So of course, in the optimal solution, we set our variables yjk in some way. In the optimal solution, D will be set in order to be equal to the minimum value of any bundle, because we're trying to set it as high as possible, but we hit the ceiling, which is the minimum among all of these values because of that constraint. But again, in the optimal solution, because we try to push D upwards, it will be set to the ceiling, which is the minimum value of any bundle. And therefore, in the optimal solution, D will actually be equal to the minimum of all of these, which is exactly this optimization objective. Right? And the idea is what the solver will try to do will be to set the variables yjk in a way that when I then push D as far as possible, this value will be as high as possible. That's exactly the same as maximizing the minimum value of I for any bundle. Okay, so this is, I think, like a really nice trick. Maybe surprising if you haven't seen integer programming before, because it's an objective that seems to be inconsistent with the framework, and yet we can capture it pretty easily in this powerful formalism. Okay, so again, Bender is just emphasizing this point that max-min and min-max can be expressed as linear objective functions and linear constraints, which really sort of increases the power of integer programming. But now let's say that I want to find a maximum share allocation that gives each player his maximum share guarantee. How would I do that? So that's actually really easy. Yeah.
Can you clarify again what is the problem with this? So we want somehow like the general division of the goods, such that what holds?
Oh, sorry. So great question. So the question was, so what do I want to satisfy in my allocation? And the answer is, I want each player to get at least a value that's at least his maximum share guarantee. Okay, so basically each player has this maximum share guarantee, which is what he could guarantee if he divided the items. And then I want to allocate the items in a way that the value of each player for his bundle is at least his maximum share guarantee. Okay, good point. Okay, is it clear what we're trying to do, what the fairness guarantee we're trying to satisfy is? So we just want to give each player at least that value. Great question. So the question was, is it necessary that such an allocation exists? Unfortunately, the answer is no. However, it's extremely difficult to find examples where one doesn't exist. So for years, people thought that it always exists. And there are counterexamples, but they're very, very intricate. So in practice, I'll talk about like the real world practice of this in a minute. In practice, we've never seen an example like that people have given of real world values that doesn't admit this kind of allocation. Okay, so unlike envy-freeness, where in many real-world examples you won't have an envy-free allocation, in this case, in order to find an example that doesn't admit this maximum share property, you have to come up with really, really, really contrived examples. So in practice, you can always get this thing.
Is it necessarily true that every person is going to report this valuation to the committee? Is there an incentive not to do that?
Yeah, that's a great question. So we haven't really talked about algorithms, right? We just talked about fairness notions. But for the algorithms that are used in practice, they do not satisfy this property called strategy proofness, which means they're immune to manipulation. We'll come back to this kind of stuff when we talk about game theory. I can talk about this for a long time. The short answer is that it's not a big deal in practice. The kind of application I'll show you in a minute. Because people, what these applications try to do is tell people what the fairness guarantees are, but people don't know how the algorithms work. And without knowing how the allocation rule works, it's very easy to manipulate in order to give yourself a better outcome. So in practice, on the type of applications that I'm interested in, which is helping small groups of people, solve these type of problems, it's actually not a big deal. Okay, so let me, I guess I'll just use my last 2 minutes to tell you about the application and we'll wrap up. So, one example application is that's very, very close to my heart is Splitit. It's a Fair Division website that we launched in November 2014. It's not for profit. And the idea is, the high level idea is to give provably fair solutions to everyday fair division problems. It builds on quite a bit of literature on fair division, but also more and more on algorithms that we developed here at CMU. And so far, it's been used by around 100,000 people. So it's like pretty, people care about these problems and actually use this kind of thing. Right now, it has 5 applications for dividing rent, fare, credit, goods, and tasks. And let me just mention, for goods is the stuff we talked about. Rent, the goods, we didn't get to like the algorithms actually used right now. We didn't have time for this, but they're also based on integer programming. So goods is based completely on integer programming in a way that gives fairness guarantees that we can always guarantee no matter what. Okay? Rent division is based on linear programming. So basically the algorithm is, solves multiple linear programs and is based very heavily on that. Tasks is also completely based on integer programming. And the other 2 applications are not linear or integer programming. But the point is, 3 of the 5 applications rely very heavily on the kind of approaches and techniques that we talked about in the last 2 lectures. Okay, so again, like even if you think about these problems of fair division, how do housemates divide the rent? These are things where you can, find algorithms that give you provable fairness guarantees. And to get these guarantees, the best way to do it in practice is with linear programming and integer programming. Yeah.
What are the parameters in the rent case that's different than just divide by the numbers?
So the only thing is the parameters are the value each player has for every room. Right? So basically the idea is there is a total rent for the house, and every player has a value for each room. The only assumption is that the values add up to the total rent, and then you can actually get a completely envy-free solution in this case. Yeah. So that's elicited on the website. So the website has an interface where every player, there are these sliders, and they just use the sliders to specify their value for every good or every room in Red Division. In goods, it's very easy because of the additivity assumption. The only thing you need to specify is your value for each good. So the elicitation is pretty easy. Yeah, let's take it offline because we're out of time. Okay, so we'll see you guys on Monday.
Is it open source?
It is, yeah.